Problems in Chapter 19 can be solved very similarly to the problems in Chapter 18. The only main difference here is instead of just beginning with a single concentration of your acid or your base, now you're going to be exploring the whole concept of a buffer. And so in a buffer, you have a combination of your acid or your base, and then the conjugate salt in order to kind of make these things a little bit different than just the normal acid-base equilibrium we explored in Chapter 18. But the great thing is because we're still looking at acid-base equilibrium, there's only one small change that we have to make to our whole overall scheme. But after that, everything is exactly the same. And so for this problem, I'm asking you to determine the pH of a solution. It is 0.2 molarity acid and 0.3 molarity of your sodium acid, and the Ka is 2.5 times 10 to the negative 5. And so here again, that HA is just my generic form of any type of weak acid. That NaA is going to be a sodium acid, or whenever you kind of plug this stuff into water, that sodium breaks off, and so you're just left with the conjugate base of your acid. And so same kind of setup when it comes to these problems. If we are given initial concentrations and we want to know something about equilibrium concentrations, we have to have a Rice table. And so we'll create our Rice table, fill it in the same way that we did in the past with a slight change. But after that, again, everything else is just the same. And because we're given a Ka value, writing down the equation for Ka will allow us to, again, solve for an X, plug those values into our Ka equation and solve for whatever we're looking for. So let's begin with our first thing, where we're going to have our Rice table. And so as I stated in the many times in the previous videos, our acid is going to be dropped in water and it's going to reach a reversible equilibrium with the products of H3O plus and our A minus. A minus is the conjugate base of our HA. And so as I mentioned before, this is our HA. This right here, the sodium A, is going to break apart into sodium ions and A minus. So that is what we're going to be representing with our A minus. In addition to that, right off the bat, we know we can use a Ka equation because we're given the value of Ka. Why not use it to our advantage? And so here we know that our HA is 0.2. We know our H3O plus is 0. But something that is a little bit different than what we've seen in the past is now we actually have an initial concentration of our A minus. In previous problems, we didn't have any additional substance that can kind of contribute to this A minus. The only, thing that your A minus was coming from in just the basic acid-base equilibrium problems is just whenever HA decomposed to create your H3O plus and your A minus. But for this problem, I'm adding an additional substance that contains this A minus. And so initially, this is no longer going to be 0 because I am throwing stuff into this mixture that contains this A minus initially. And so when we kind of go through and look at these types of problems, the next step happens the exact same way it's happened all the other previous times. And so your HA is going to decompose and produce one H3O plus and one A minus. And so the minus X and the plus X and the plus X still remain exactly the same as they did in the previous steps. And the equilibrium is still going to be your initial minus the change, or initial plus the change, initial plus the change, or we know that our HA concentration at equilibrium is going to be 0.2 minus X. Our hydronium concentration is just going to begin at 0. It's going to change by whatever X is to equal X at the end. Our A minus is going to be our initial concentration plus whatever amount that's going to break up from HA to produce A minus is going to come in there. But if you try to plug all of this information into your Ka equation, you're going to have to be solving for a lot of different X's. It's going to become a nightmare. But one thing that will help us all out is same kind of idea from the previous chapter, is we can assume because our Ka is times 10 to the negative 5, this is a very small Ka value. Well, relatively small. And so in that case, we can assume that the change in equilibrium of our HA and the change at equilibrium of our A minus is going to be very negligible when it's related back to this initial concentration of 0.2 and 0.3. So therefore, let's just do this and get rid of them altogether. And so now our life becomes a whole lot less complicated. So we know our Ka is 2.5 times 10 to the negative 5. Now we know that our hydronium ions, we can plug in for X. We know our A minus is actually a real value now of 0.3. Our HA is a real value of 0.2. So plug these into your equation and solve for X, and we end up with 1.7 times 10 to the negative 5, which equals the concentration of your hydronium ions. And so in this problem, we're asking you to solve for pH. So the last step we're going to be exploring here is what is the relationship between pH and our hydronium ions. And so it's that lovely equation, pH equals negative log of your hydronium ions to give you the pH here of 4.8.